In this video, I'm going to show you how to find the area bounded by a polar curve. Remember that a polar curve just gives us the radius r as some function of the angle theta. To find the area under a polar curve, we can think about breaking up the polar curve into a bunch of really small sectors of circles. Each sector will have a radius r and span an infinitesimally small angle d theta. The area of the sector is then given by a half r squared d theta, and to find the total area under the curve, we can integrate up all these areas of sectors. So the area of the curve is the integral of a half r squared d theta. This is the formula that we're going to be using for the coming examples in which we find the area bounded by polar curves. Here's an example of finding the area bounded by this polar curve. This polar curve looks like a flower with a bunch of petals, and we want to find the area for theta between 0 and pi over 4. So that's just this petal here. We want to find the area of that petal. So in order to do this, we're going to use that integral that we just derived. Area equals integral of a half r squared d theta, and then we're going to put in our bounds for theta and substitute for r. So putting in our bounds for theta, we've got bounds 0 to pi over 4, and then substituting for r, we've got from 0 to pi over 4 a half sine squared 4 theta d theta. Great, so now we just have to compute this integral and we'll have the area. But this is actually the tricky part, computing the integral, because this sine squared 4 theta term is difficult to integrate. Sine is easy to integrate, but sine squared is not easy to integrate. So in order to integrate this, we're going to have to express this sine squared term a little bit differently. We're going to have to reduce the power on that sine squared. And to reduce the power, we're going to note on the side here that 2 sine squared of some number x, we're going to always write that as sine squared x plus cos squared x minus cos squared x minus sine squared x. And using our trig identities, we can write this sine squared plus cos squared, that's just 1, and then this cos squared minus sine squared, that's just cos 2x. So we can say that sine squared x equals 1 minus cos of 2x over 2, and that's known as the power reduction formula. So in this situation here, we've got 4 theta as our angle. So we're just going to use the power reduction formula with x equals 4 theta. So then we get that sine squared of 4 theta equals 1 minus cos of 2x. So x is 4 theta, so 2x is 8 theta. Got to double it. All over 2. And so now we're going to go ahead and substitute that in, and the integral is going to be a lot easier to compute now. So that's the integral from 0 to pi over 4 of a half times substituting in this expression here, 1 minus cos 8 theta over 2 d theta. And now let's go ahead and compute this integral. So that's equal to from 0 to pi over 4, a fourth minus cos 8 theta over 4 d theta. And we can go ahead and take the antiderivative now. That's just a fourth theta minus sine 8 theta over 32. Theta going from 0 to pi over 4. So evaluating at pi over 4, we've got a fourth pi over 4 is pi over 16, then minus sine of 8 times pi over 4 is 2 pi over 32, then minus evaluated at 0, so that's just 0 minus sine of 8 times 0 is 0 over 32. So simplifying even more, that's pi over 16 minus, well, sine of 2 pi is 0, so this whole term is 0. minus 0 minus sine of 0 is also 0, so that's also 0. So it's really just pi over 16. So that is our area. Gonna box it really big. Yep, that's the area of that petal right there. Here's another example of finding the area bounded by a polar curve. For this curve, we want this section inside, and the way we're going to find the area of that section is just like before. We're going to set up the area integral. Area is the integral of a half r squared d theta, and we'll plug in our bounds for theta, 2 pi over 3 and 4 pi over 3, and then we'll just substitute in for r and evaluate the integral. So let's go ahead and do that. I'm not going to write the bounds until the very end just because they take up a lot of space. So just remember that they're still there. Okay, so a half r squared, r is 1 plus 2 cos theta squared d theta, and we'll go ahead and expand out that squared. So that's 1 plus 4 cos theta plus 4 cos squared theta d theta. And we'll go ahead and distribute through our 1/2. So it's a half plus 2 cos theta plus 2 cos squared theta d theta. Alright, so we want to evaluate this integral. A half is easy to integrate, 2 cos theta is easy to integrate, but this 2 cos squared theta term is not easy to integrate. Cos is easy to integrate, but cos squared is not. So we're going to have to do something like before. We're going to have to use a power reduction formula on cos squared theta. So how we get the power reduction formula for cos squared theta is we can start out by writing 2 cos squared theta equals sine squared theta plus cos squared theta, then plus cos squared theta minus sine squared theta. That way, our sine squareds will cancel and we'll just be left with 2 cos. And now we can use our trig knowledge, our knowledge of trig formulas, identities, to simplify this. Sine squared plus cos squared is just 1, and then plus cos squared minus sine squared, well, that's just cos of 2 theta. So we can say that cos squared theta equals 1 plus cos 2 theta over 2. And that's our power reduction formula for cosine. Okay, so we're going to use this formula to reduce that power of the cosine squared and make the integral something we can actually compute here. So let's write this integral again, but this time plug in our cos squared theta equals this. So I've got a half plus 2 cos theta, and then plus, well, this 2 is going to cancel out with the 2 in the denominator, so we just have 1 plus cos 2 theta d theta. Alright, so now let's simplify this. That's integral of half plus 1, that's 3 halves, plus 2 cos theta, plus cos 2 theta, and now we're good. We can actually integrate this thing now. So let's go ahead and integrate that. That's 3 halves theta, plus 2 sine theta, plus a half sine 2 theta. And we'll bring our bounds back from up there, 4 pi over 3 and 2 pi over 3. And now it just remains to actually compute the difference at the bounds. So to give us a little bit of space, let's go ahead and do that over here. So okay, so first plugging in 4 pi over 3, 3 halves times 4 pi over 3 is 2 pi, and then we've got plus 2 sine 4 pi over 3 plus a half sine 2 times 4 pi over 3 is 8 pi over 3. And that's all minus 3 over 2 times 2 pi over 3 is just pi, and then plus 2 sine 2 pi over 3, and then plus a half sine 2 times 2 pi over 3 is 4 pi over 3. All right, let's put a little border there so we don't get confused. Okay, so now let's go ahead and evaluate this. So 2 pi minus pi, that's just pi, and then 2 sine 4 pi over 3, and then minus a half sine 4 pi over 3 is just 3 halves sine 4 pi over 3, and then we've got our plus a half sine 8 pi over 3. We can convert that to a simpler angle. 8 pi over 3 is equivalent to 2 pi over 3. And then we've got minus 2 sine 2 pi over 3. Okay, so now let's simplify this even more. So we've got pi plus 3 halves sine 4 pi over 3, and then a half sine 2 pi over 3 minus 2 sine 2 pi over 3 is minus 3 halves sine of 2 pi over 3. All right, let's go ahead and evaluate the trig functions. So 3 plus 3 halves times negative root 3 over 2 minus 3 halves times root 3 over 2, and that's equal to pi minus 3 root 3 over 4 minus 3 root 3 over 4 again. So that's just pi minus 3 root 3 over 2. And that is our final answer. That's the area of the region. In the future, when we do more of these problems, we're also going to learn how to find the bounds of integration on our own if we want to pick out a particular region in the graph.